Yeah, some example. The first is easy. If you have a meta-analysis with these 6 study results, yeah, you see at first sight there is an intervention effect. Okay, there's one study which is not significant, but this study is very small. All others have a significant effect. It's very clear that here the intervention is useful. But if you do a meta-analysis, the advantage is that you have a confidence interval and have also see in a graphical way how large the estimation uncertainty is. So also you see at first sight that there is here that the intervention is useful and beneficial. It's better to do a meta-analysis. Yeah, next example is a bit less clearer. Yeah, what do you think? Do we have a significant effect also here in this situation, or would the pooled effect estimate cross this line? Yeah, the poll is running. Clearly yes, and it's unclear. It's head-to-head. I think, yeah, we can stop here. About more than 40% think clearly yes, more than 40% think it's unclear, and about 10% think there's clearly no effect. The answer is here yes. You can conclude there is an intervention effect, and it's very clear that also we have now 3 studies which are not significant, but the most evidence lies here, and this yielded in this pooled effect estimation. And here it's very clear that we have an intervention effect. Example 3 is also unclear. Yeah, another poll, please. What do you think now? Clearly yes, clearly no, it's unclear. Oh, still a number of people say clearly yes. Majority now say it's unclear. And yeah, this would be the right answer here. It's not clear. You have to calculate the meta-analysis. Yeah, this is the answer. It's very tough, but the confidence interval includes the null effect. So from these pooled effect, you see there's no proof of an intervention effect, even if you use a fixed effect model. If you would use a random effects model, the confidence interval gets larger. But even with a fixed effect model, it's not statistically significant. Example 4, it's application of the random effects model in a clear data situation. Yeah, most studies are significant. Of course, the pooled effect estimate is significant. Yeah, and you have the prediction interval showing that there is some heterogeneity. Again, this red area here is a range which includes with high certainty the true effect of a single study, which is similar to these 6 studies. So this is the average with estimation uncertainty, and this is a range of a true effect in one of these studies. So in a less clear data situation, it may be that from the confidence interval you can conclude there is an effect. but this refers to the average. The prediction interval includes the zero effect, so you still can conclude that the intervention is beneficial on average, but you have to keep in mind that due to heterogeneity, study situations can be expected where the intervention has no effect. No? So on average, yes, but heterogeneity is large, and this you have to keep in mind and include this in a discussion, for example. But the conclusion is there is an intervention effect. So how do we use the concept of conclusive effects? Here we have very large heterogeneity, an I-square of about 70%, and a clearly significant Q-test. And but nevertheless, all studies are significant, but with large heterogeneity, you can use the prediction interval to say, okay, we have here a situation with clearly conclusive effects. So we have a proof of an intervention effect, but the effect size is unclear and heterogeneity is large. This you can conclude even if it's not meaningful to perform a meta-analysis. Here's a situation with moderately conclusive effects. You have a conclusive data situation because most of the evidence is lying on this side, but the prediction interval includes a zero effect, which means that you have conclusive effects, but they are only moderately conclusive. So the decision whether the intervention is beneficial or not, is now dependent on the certainty of the study results. If you have RCTs with low risk of bias, you can say there's at least an indication of a beneficial effect. But if you have non-RCTs with high or unclear risk of bias, you may conclude there is no proof of intervention effect. This depends on the situation. So example 8, no conclusive effects, very large heterogeneity, some evidence is lying here, some is here, and here you have no proof of an intervention effect. So now let's look more closely to the problems which we have additionally if we have a meta-analysis with very few studies. The choice between fixed effect and random effects is very difficult here because the tau cannot be adequately estimated because you have only 2, 3, or 4 studies. And this is similar to the situation where you want to use a t-test and have only a sample size of 4 people, for example. The problem in this situation is that the confidence intervals of Decimal and Laird are too narrow, do not hold type 1 error. The confidence intervals of Hart and Knapp, Siedig-Jonkman, a method which you want to use if you think that the random effects model would be the right model. These confidence intervals are very wide or even non-informative, and you have to deal with the additional problem of Hart and Knapp, Siedig-Jonkman, that in homogeneous data situations, the confidence intervals are sometimes too narrow. Here's an example from an IQWiC report. You have 2 studies, both are statistically significant. So this is a situation with clearly conclusive effects. Here's a confidence interval of Decimal and Laird. And here's the result of a fixed effect model. This is not very close together, but this is the result of Hart and Knapp, Siedig-Jonkman. And you see clearly that Hart and Knapp, Siedig-Jonkman is very conservative. And to use this model and this method and decide that there is no added benefit because this is not statistically significant would be critical, because you have both studies are statistically significant. And if you would have only the first study, you would interpret these results and conclude there is an effect. Okay, for a proof, maybe you need replication and need a second study, but at least there's an indication of a benefit. Now you have a second study, and this is also significant. And then to conclude based on this meta-analysis, no, there is no proof of an effect. You cannot communicate this, and this is critical. So we need other methods to deal with this situation. Another example with 3 studies. Again, all 3 studies are significant. Here's a result of Desmond and Laird. Here the result of Hart und Knapp, Siedig-Jonkman. And again, Hart und Knapp, Siedig-Jonkman is very conservative. And this is not only a problem with 2 studies. You have the same problem also when there are 3 studies. So let's look at this ad hoc variance correction. We have 2 studies, both are significant. And in this case, Hart und Knapp, Siedig-Jonkman, without correction or with ad hoc correction, there's no difference. Of course, both methods are very conservative. The ad hoc variance correction is not required here. And now what I do in the next slides is that I move the second studies in small steps to the left. That means I make the data situation more homogeneous. So what happens now? Here there is a large difference between Hart und Knapp, Siedig-Jonkman without and with correction. So the Hart und Knapp, Siedig-Jonkman confidence interval width decreases with increasing homogeneity. But yeah, if you use the variance correction, then it gets larger again. And the question is the use of the ad hoc variance correction now required or not? So we need a procedure for this. So in this case, this is very strange because Hart und Knapp, Siedig-Jonkman, also holding type 1 error on average, is now smaller, the confidence interval width, than that of Desmond and Laird. And this is strange because we know that even this interval is too narrow. And this is even more narrow, and this is clearly wrong. This means in this case, it's clear that we need the variance correction, because this result is simply wrong. And this is our proposal published in the article by Schulz and colleagues. And this proposal is based on further suggestions by Guido Schwarzer, Gerta Rücker, and Dan Jackson, that for the decision whether we use the ad hoc variance correction or not, we compare the Hart und Knapp, Siedig-Jonkman method with that of Desmond and Laird. And if the confidence interval of Knapp-Hartung without correction, if the width is smaller than that of Desmond and Laird, then we use the variance correction. In this case, we would do a qualitative summary of study results because this is over-conservative. But for the decision, whether we use the ad hoc variance correction or not, we compare it with Desmond and Laird. So here's an overview of the whole procedure, how we decide which model we use for meta-analysis. And in the first step, we use the PICOS framework to decide which model we use. In general, we use the random effects model because we say that in general heterogeneity has to be expected. Only in the case of two studies, we use in general the fixed effect model, unless there are clear arguments not to do this. A clear situation where this model is justified is, for example, if you have studies with identical design, then this assumption is plausible and we can use it. And in general, we use this model as standard in the case of two studies. I come back to this point a little bit later. Then step two, of course, we evaluate heterogeneity. This is a mandatory step in any meta-analysis. Of course, if you can, the best thing is you can explain heterogeneity and split the whole study pool into subgroups, for example. But here I consider the case that the try to explain heterogeneity is already performed, and we only have unexplained heterogeneity. And if this is too large, then quantitative meta-analysis is not useful. And in this case, we perform a qualitative summary of study results by means of the concept of conclusive effects. For the evaluation of heterogeneity, yes, we use the Q-test, I-square, and the visual inspection of the forest plot. Then in step 3, we make a final model and method choice. If we chose the fixed effect model in the first step and find now here in step 2 very strong heterogeneity, which is unexplained, then we reconsider the preliminary choice and maybe we switch to the random effects model. If we keep the fixed effect model, we use inverse variance for continuous data, or Mendel-Hansel in the case of binary data. In most cases, we use the random effects model, which means we use Hart und Knapp Siedig-Jonkman with or without variance correction. Yes, for this we compare it with Desmond and Laird, and we compare it with a qualitative summary. And in a lot of cases, in with few studies, at the final end, we end up with a qualitative summary of study results, because a fixed effect model should not be used, because heterogeneity has to be expected. And Hart und Knapp Siedig-Jonkman is not useful because the confidence interval is not informative. Then we will end up with a qualitative summary. This is an overview of the whole procedure. Probably there are questions regarding this, but let's go through the next examples. I hope that it gets clearer when we go through these examples. This is also from an IQWiC report. We have a situation with 3 studies. All are not significant, but most of the evidence is lying here on the benefit side. So first question is, we have 3 studies. One to perform a random effects meta-analysis by means of Knapp-Hartung Siedig-Jonkman. Do we need the variance correction? We compare Hartung Knapp Siedig-Jonkman, which is here, with the result of Desmond and Laird, which is here, and we see, oh yes, the confidence interval width of Hartung Knapp Siedig-Jonkman is smaller than that of Desmond and Laird. This means we need the variance correction, and this is then the result. And this confidence interval is not non-informative, because it's not wider than the union of the single confidence intervals. So here in this example, we would use Hartung Knapp Siedig-Jonkman with variance correction, and the conclusion is that here in this situation, we have no proof of an effect. Another example, again, 3 studies, but now 2 studies are significant and 1 is not. Here's the result of Hartung-Knapp-Siedik-Jonkman. The confidence interval is not smaller than that of Desmond and Laird. So, and it's also informative, but here we have the difficult situation. We have 2 results. We know Desmond and Laird is significant, but the width of this interval is too small. We have Hartung-Knapp-Siedik-Jonkman. It's not significant, but this interval maybe is too large. The way out of this problem is to use the qualitative summary of study results. And here we use the concept of conclusive effects. And here we have conclusive effects because we have 2 significant studies, and the majority of weights is from the significant studies. So based on the concept of conclusive effects, we say, yes, we can conclude that there's a benefit of the intervention, but the disadvantage is the effect size remains unclear. But to decide there's no effect based on Hartung-Knapp-Siedik-Jonkman seems to be too conservative. It's better to say there is an effect, but we cannot say something about the amount of the effect size. Third example with 4 studies. Here we have a situation. Hartung-Knapp-Siedik-Jonkman is also informative. We do not need the variance correction. Hartung-Knapp-Siedik-Jonkman, maybe the confidence interval is too large, but we have the result of Desmond and Laird, which is also not significant. We know that this interval is too small, but if even the too small interval is not significant, then we can, based on both methods together, we can conclude there is no proof of an effect. Because even if you use a method where the confidence interval is too small, if even this is not significant, then there is no proof of an effect at the final end. This is the way we perform meta-analysis within IQWiG currently. Let's discuss some important points. I think it is obvious that we have no satisfactory standard method that it's currently available to perform meta-analysis in the case of very few studies. There is no unique method which we can use all the time. The fixed effects model is possible in practice, but has limitations. It does not hold the type 1 error if in fact there is heterogeneity. Therefore, in general, we use the random effects model, unless there are clear reasons to justify the use of the fixed effect model, like the situation that all studies have the identical design. We have to deal with the problem that the random effects model frequently has low power or does not even yield informative results. In the case of 2 studies, despite of the general recommendation, we use the fixed effect model as standard, unless there are clear reasons against the use of the fixed effect model. And the reason is, in situations where we have only 1 study, we make conclusions based on this study. In principle, this is an application of the fixed effect model. And simply because you have 2 studies, then to switch from the fixed effect to the random effects model, this step seems to be much too large. We are doing this step from 2 to 3 studies, but not from 1 to 2 studies. This is the reason why we use, for practical reasons, the fixed effect model as standard approach in this situation of only 2 studies. Yeah, in the case of 3 or 4 studies, we use the random effects model. Again, unless there are clear reasons to justify the use of the fixed effect model, we use Hartung-Knapp-Sietig-Jonkman with checks regarding variance correction, and we look whether the results are informative. That means we apply Hartung-Knapp-Sietig-Jonkman without or with variance correction, or we switch to the qualitative summary of study results if this does not lead to useful results. For the qualitative summary, we use the concept of conclusive effects and prediction intervals. But there are 2 other promising possibilities, namely the Beta-binomial model and the Bayesian meta-analysis with informative priors for tau. So this is the outlook. We'll go quickly through these two models. The Beta-binomial model is only suitable for binary data. We have performed a simulation study in collaboration with Tim Mattes from Göttingen and Oliver Kuss from Düsseldorf. Results are recently published. Summary is that this model has no advantages in the case of 2 studies, but it has more power than Hartung-Knapp-Sietig-Jonkman in the case of 3 to 4 studies. And this means we currently consider to include this model in our procedure I described before. So it has a little bit more power, but not in a dramatic way that it solves all the problems. So we have to look for alternative methods, and another promising method is that of Bayesian meta-analysis. The usual way to do Bayesian methods would be to use non-informative priors, but in this case you have the same problems than before, namely in the case of 3, 4 studies, not enough power. But if you use informative priors, not for the intervention effect, but for the heterogeneity parameter, then you can see that the Bayesian meta-analysis is a good compromise between Desmond and Laird and Hartung-Knapp-Sietig-Jonkman. This is a project in collaboration with Tim Friede and Christian Röver from Göttingen. There are suggestions for prior distributions for tau in the literature, but we wanted to know what is the correct prior information for applications in health technology assessments. So we started a project and derived empirical priors for tau from our own meta-analysis. You can get some more information about this in these slides. I think they're all available on the training Cochrane site. This is a webinar from May 2021, where we have summarized this project. Currently, we are busy with estimation of the empirical priors by means of a hierarchical Bayes model proposed by our colleague Christian Röver. And now we prepare a manuscript with suggestions of priors for tau for the effect measures risk ratio, odds ratio, hazard ratio, SMD, suitable for applications in health technology assessment. The preliminary results are in this way that indeed the Bayesian meta-analysis is a compromise between Desmond and Laird and Knapp-Hartung-Sietig-Jonkman. There are some few situations where we also have to switch to a qualitative summary of the results, but the advantage of using Bayes with informative priors would be that we have much more situations where we are not able to perform meta-analysis based on Hartung-Knapp-Sietig-Jonkman because this confidence interval is very wide and contradicts with the qualitative summary of study results. But if you use Bayes with these informative priors, we have a useful result, and we can, additionally to the conclusion that there is a benefit of the intervention, we can also quantify this effect, and this would be the advantage of using Bayesian methods in the future. So a summary, I have to hurry up. Evidence synthesis in the case of very few studies is problematic. In any case, if there's too large unexplained heterogeneity, you have to perform a qualitative summary of study results. This is the same also with when you have many studies. But if you have only few studies, you have additional problems. In 2 studies, we use as a pragmatic approach a standard model, the fixed effect model. When we have 3 or 4 studies, we use the random effects model with Hart und Knapp Siedig-Jonkman, without or with variance correction, or we use the qualitative summary if Hart und Knapp Siedig-Jonkman yields no useful information. If we have 4 studies or more, 5 studies or more, we use the random effects model, also with Hart und Knapp Siedig-Jonkman, and in the future, we consider to include the Beta-binomial model and the Bayesian meta-analysis with informative priors for tau coming from empirical priors based on our own meta-analysis. So conclusion, we have no satisfactory universal standard method for meta-analysis in the case of very few studies. Additional approaches, Beta-binomial, Bayes are under consideration, but the procedure we currently use in IQWiC, which is a combination of the fixed effect model, the random effects model, and the qualitative summary of study results, at least represents a feasible approach to perform evidence synthesis with useful results in the case of very few studies in practice, but hopefully can be improved by means of these 2 additional approaches in the future. So thank you very much for your attention.